Your first activity here in this unit was to read about energy, specifically looking at storage and transfer. I just want to kind of go over some of that information real briefly, just to make sure we don't have any confusion on it. So when we talk about energy, the first thing we want to understand is energy is really simply the ability of matter to change. So in order for matter to change, it has to have energy to do so. No change in matter can happen without a corresponding change in energy. So to change energy, you have to, one, be able to store energy, and two, you have to be able to transfer energy. And so that's what we want to kind of look at throughout this little video. Before we kind of get too much into transferring and storage, I do want to give us a little bit of a note on temperature. Temperature is one of those things we kind of lie to you about, and we say it's all about the speed of the particles, and all the particles have the same speed, and that's really a major lie. When it comes to temperature, temperature is really something that tells us the average motion of the particles. It is just that. It is a statistical average, meaning you might have a couple particles that have a very specific motion, but actually what you end up with is a group of particles that have a lot of motions, both high and low. As you can see, when we look at the temperature curves here, the lower temperature has a much higher peak, meaning on average the particles are moving slower, but it also has a very, very high amount of energy as well. So there are particles that have high energy, there are particles that have low energy. When the temperature goes up, that curve flattens, and you now get a wider range of motions, but you get a larger proportion of motions that are at a higher temperature. So again, when we talk about these at all, what we're really talking about is a mix of high and low energies. We talk about that because when we talk about transferring energy, the main one we're going to focus on is the idea of heating. Heating is the transfer of energy through the collision of particles with different kinetic energies. Now, if you think about this, if you have two systems at different temperatures, there's an overlap. So there are some particles in the low temperature that are going fast, and there are some particles in the high temperature that are going slow. If a high energy particle hits a low energy particle, it is going to transfer energy towards the low energy particle. The high energy particle is going to get slower, the slow energy particle is going to get faster. So if there's all these different temperatures, really what we're saying when we're talking about heating is that higher energy particles transfer energy to lower energy particles, but energy transfers faster from high temperatures to low temperatures. Energy goes both directions. This kind of goes back to diffusion. Particles don't know where they are. They don't have a decision to make. They just kind of travel randomly. Energy is kind of the same way. Energy transfers randomly. It doesn't know that it's at a high temperature or a low temperature. But what happens is the energy goes both directions, but because there's a lot more particles with high temperature or with high energies at the higher temperature, the energy is faster transferred down to the low temperature. So something I want you to understand is that energy always is going in both directions, just like in diffusion. Particles are going both ways. They just tend to seem like they're going faster in one way than the other because of statistics. This is why if you're going to get into sciences, especially chemistry, biology, statistics is a great class for you to go into. All right, so let's say we're transferring energy. We now need to store it in places. The two that we're really concerned about are thermal, which is motion of the particles. This is kind of the active storage. Faster particles store more energy, slower particles store less energy, and it is directly related to temperature. If more energy is stored in motion, then the temperature has to go up. If less energy is stored in motion, then the temperature has to go down. And that's a pretty simple concept there. When it comes to phase, we're talking about the position of the particles, and it has a lot to do with the attractions that the particles have for one another. And what we simply say is that free particles store more energy than trapped particles. And that should make sense. If you want freedom, you need energy. If you want to just sit on your couch and do nothing, you don't need energy. Freedom requires more energy to be stored in your system because you have to be able to overcome those attractions. If your particles aren't free, they're not overcoming attractions, and therefore they don't require stored energy. Last part I want to kind of look at in this very kind of rambled presentation is I want to look at a specific change of state. So what we have here is a solid becoming a gas. And we can see our particles up here along the top. Excuse me. And what we can kind of see is that to begin with, we have a solid material. All the particles are nice and orderly, kind of trapped near one another. As we add energy, as we increase the energy content, we see the temperature rise. That's an example of thermal energy being stored in the system. We then again see that over here in stage 3 and then in stage 5. Stage 1, stage 3, and stage 5, because we see the temperature going up, the energy is stored in the thermal account. The particles are moving faster. The two parts that kind of become a little bit unclear are stage 2 and stage 4. Here what we have is the transition between a solid and a liquid. Notice the temperature is not changing in either one of these, whether I'm going from a liquid to a gas or a solid to a liquid. This is because the energy that is being added to the system is not being used for motion, it is being used for position. And so we're changing from stage 2 and stage 4, we're changing the position of the particles. We're moving from this ordered state to a chaotic state, and then we're moving from a chaotic state to a completely free state. If we were to reverse this process, we would simply see the same exact graph, it would just be going down. Anytime you see a state change, you're going to have flat lines. And this is something we're going to look at in the next couple weeks to make sure that we understand exactly what's going on in those circumstances.